Francesco for inviting me to give this talk, which is the last talk of the year. So I'd like to talk about some work I've been doing in the last about 2 years, in most part with Patrice Keul from UC Davis and Marc Delarue for part of this work, who is at Institut Pasteur. Patrice Keul has been a regular visitor here, and he gave a talk already slightly on this subject 1.5 years ago, I think. So there will be some overlap with his talk and also some new advances in the work on this topic. So the outline, I will first explain what are the problems, assignment and matching problems. I will then go to optimal transport with variable masses, and then I will touch a few words about optimal transport with the Gromov-Wasserstein distance, which is work in progress. So optimal transport and assignment problems have a long history. They started by Gaspard Monge, the famous Monge. It was the assignment problem, which I will discuss thoroughly in the next few slides. Then Erwin Schrödinger, our father, all of us worked on this problem. There is the so-called problem of the Schrödinger bridges, which is the problem to find what is the stochastic pathway between two given probability distributions. The great names associated to all these problem of assignment, transport, etc. Leonid Kantorovich, and then more recently in France, we have Cédric Villani and Alessio Figali. And essentially, it was introduced as the study of optimal transportation and allocations of resources. So I'll give a first example, which is the problem of optimal transport. One of the first ways it was proposed is the assignment problem. So initially it was proposed by Monge, and it was dealing with mines and factories. But I will translate it to a French version, which is with bakeries and mills. So assume you have Paris here in the 18th century, and you have, let's say, 5 bakeries, 1, 2, 3, 4, 5, spread throughout Paris, and the bakeries need flour to make the bread. Then you have mills, A, B, C, D, E, and the mills produce some flour, and the flour is to be used by the bakeries. And then there is a cost matrix, which tells you what is the cost of transportation of the flour made by mill number I to bakery number J. So this transportation cost can be represented as a matrix where lines and columns represent the cost from line I, from mill I to factory to bakery J. And the idea is, how do you assign to each mill a bakery so that the total transportation cost is minimal? So obviously in this case, you draw arrow, each mill is associated with one bakery, and you associate this arrow so that the total cost will be minimal. In that case, it's the green line. So you have mill A associated with bakery 1, mill B with bakery 2, mill C with bakery 4, etc. And the total cost, you can see, is 10.5. And this is the minimal transportation cost that you can get. And this is a very important problem in operational research. And it was very much developed in more general forms in economics, data science, and physics. So actually, it regained a lot of interest in recent years because of this data science business. And of course, what you have is once you have the cost matrix on the left, the optimal assignment can be represented by a matrix of 0 and 1, where you have 1 every time in the minimal plan, when you have 1 when site I and j are connected, and 0 if they are not connected. So this is a matrix of 0 and 1. On each line, you have only 1, 1, 1. On each column, you have only 1, 1. And that's it. Okay. So the general form of the assignment problem, which is called also the bipartite matching problem or the marriage problem, is you have endpoints. You have two sets of endpoints. So endpoints on the left. There is no way I have no pointer here. Pierfrancesco, do you know how to put a pointer?
No, but so if you move your mouse, you don't see.
No, it doesn't. Okay, there is no pointer. Okay, it doesn't matter. Okay, so anyway, so you have two different sets of points of same cardinality, endpoints on the left, endpoints on the right, and you have a matrix which is given in advance, Cij, which is the transport cost from I to j. It's an n by n positive matrix, and the assignment. So, and then you look at all bijective assignment from the left side to the right side. So in other words, you want to find a permutation P, which minimizes the cost sum over I from 1 to n of C from I to P of I. So in other words, you have on the left 1 to n, and on the right, you can reorder them as P of 1, P of 2, P of n, and then you join them and you look for the permutation which will minimize that. So I gave the example of bakeries and meals, factories and mines. It's also called sometimes the problem of the matrimonial agency. The matrimonial agency has profiles of men, profile of women, and they fill some forms, and then they have to match all the men with all the women. Okay. And so the problem was solved by the so-called Hungarian algorithm, which was published by Harold Kuhn in 1955. And it was based on work by two Hungarian mathematicians in the 1930s. And in fact, funny thing is that in 2006, it was discovered that Jacobi, the famous Jacobi, it was published posthumously in 1890, and he had solved the problem in Latin in 1890, which is 40 years before the Hungarian mathematicians. The idea is that if you replace the cost matrix C by a matrix D indexed AB by adding two rows and lines, so A of K, B of L, then for any permutation, the total cost of any permutation K, you see that when you do the sum, you will get this sum over AK, sum over BL. And so the idea of this Hungarian algorithm is to shift rows and columns to get a simpler cost matrix by doing so by shifting one same element to each line and each column, you can bring some of the matrix elements to 0. And by doing that in a repeated way, with a given algorithm, which I don't want to explain because it's a little bit too long, you get the exact solution of the problem. So the interesting thing is that the complexity of this algorithm is of order n cube, which means that in the generic case, if you want to solve exactly in the worst case scenario, that's what people call, if you want to solve a generic assignment problem of size n by n, it will take you of the order n cube operations. And therefore, for a very large problem, it becomes quite impractical. But still, it's polynomial. And it's interesting to note that if you look at 3 matching or 4 matching, which is if you have 3 different sets of objects like men, women, and dog, and if you assign a weight to each triplet, you can solve the same problem. But in the case of n larger or equal to 3, the problem becomes NP complete, which means that there is no known polynomial algorithm to solve it. One of the other difficulties of the Hungarian algorithm is that it is serial in nature and it cannot be parallelized. So you cannot beat with standard computers, you cannot beat the order n cube practically. So that led us to come back to a problem on which I had been working many, many years ago, which is the finite temperature assignment problem, or finite temperature bipartite matching problem. This kind of problem of combinatorial optimizations were introduced by Kirkpatrick in the early 80s with the famous paper on simulated annealing. Then the statistical mechanics was introduced in a short paper by Venus and Mézard. And then I worked on it in '85, and there was a famous paper also by Mézard and Parisi. And in these cases, what we were interested at that time was to look at the quenched average problem, the disordered problem, in which, for instance, all the cost matrix, Cij, were random variable drawn from, were identically distributed random variable. And one was looking for what will be the average minimal path or things like that. But nowadays, the emphasis is more on finding efficient algorithms for specific instances, not to look for quenched averages. So the question is, given a cost function,
so
for instance,
algorithm is a bit faster than the invisible hand algorithm. It works only for assignment. It doesn't work for
way and as fast as possible.
Doesn't work. Sorry.
So the general problem can be formulated as follows. Consider, so you assume that what is given is a cost matrix, Cij, a cost matrix which is positive, and then an assignment matrix, which is a matrix Gij, which tells you if I is connected with J.
It's not this.
So Gij is equal to 0 or 1. And for any j, so for any column, the sum of the Jij on all lines, so for column j fixed, the sum of Jij is equal to 1.
Sorry.
And same for the lines, for any line
so
I, the sum of
share.
the Gij is equal to 1.
How do I share?
Which means essentially that you have zeros everywhere,
I have to
except one
sharing,
in
right?
each line and each column,
and
and only one.
How do I stop,
Once you
how
have
do I-
defined this matrix as
how do I stop
Gij,
sharing
the
here?
energy, or which I call E, which is the cost function for a given assignment matrix, is just given by sum over I and j of
Okay,
Cij,
fine.
Gij.
Okay. So now I
And
share.
the question is to find the Gij,
no,
which will
where do I
minimize
share?
this cost function.
Same,
So instead of looking for the Gij,
Sorry?
which will minimize
Oh,
the
yes,
cost
yes.
function,
Okay.
down,
we look at the partition
And,
function at temperature T,
the webcam.
which means that we look at the trace over all
What to
admissible
share?
Gij
Okay.
of e to the
Okay,
minus
the same
beta e.
screen. Share. Okay.
And therefore, we
Can
are
you see this?
led to consider
Yes,
the
so-
following partition
yes.
function. Z
Okay, so
is a sum over all configurations.
The best
So
algorithm.
configurations
So
are
the best
Gij
algorithm
equals
for
0
matching,
or 1,
for
like a
and
spin
also
variable,
for actually for
0, 1. Then you have
for
the energy
transport
e to the
are
minus
the,
beta
is the so-called
sum over I and j, Cij,
invisible hand
Jij.
algorithm.
And
This
then
is
you have to
the-
implement the
the best
constraint that
algorithm
only
as of
one
now.
Gij
And this is a
non-zero
comparison
in each
of
line,
the
and
so
one
Sinkhorn
Gij
is
is
another
non-zero
widely
in each
used
column.
algorithm.
And this is essentially
Red is this invisible
the
hand
two constraints
algorithm,
with the
and
delta
black is
functions
our
which are
algorithm.
represented here.
So we do a bit better.
Maybe I will
than,
quit this invisible hand,
this,
but this
full
is only for
screen,
assignment. It doesn't
presentation
exist in
because,
optimal transport.
I
Now
need
in
a pointer
at some point. I can
Okay. So this is
Okay,
as a function of
Francesco, I
temperature,
will,
of course,
sure.
as a function of
I will
temperature.
go back to the standard, and when I
some
need
algorithm
become
because at
extremely
some-
slow, but still
I
we
think
are
even
still,
this way it works.
better
I
than
mean,
the invisible hand.
it's fine. We
I
see
think the
Okay, so I'll
message
do it like
passing
this.
and all these
Is
are
it
not
okay like this?
yeah, but we
As far as I know, they're not
here. You don't see the pointer
and the most efficient.
Okay. So then I go back.
I'm seeing something very interesting.
Okay.
Which is
okay. So then
now we see. Now we see.
Now you see.
Yeah. Yes.
Okay, great. Okay, so I should stop. So maybe I can sharing the screen.
Remove these. Okay. So is it okay like this?
Yes. Yes.
Okay. Okay. Thanks.
Okay. What I was just saying is that Z is the sum over all configuration of
I think
assignments
if you
of e to the minus beta
like
e, the energy or total cost function,
actually, I
with the
see
constraint that it is really an assignment in the sense that for each line you have only one Jij equals to 1, and for each
just
column
above,
only
like,
one Jij equals to 2.
the time machine icon.
So then we use the standard techniques of statistical physics to exponentiate the delta functions, look for the Fourier representation of delta functions. And when you do that, of course, everything, because so you have this conjugate variable lambda and mu to impose the constraint.
Actually,
then you can do the sum
to answer
KL,
because
it's
not here. He says
decoupled
that
on
JK
on KL. And you do the sum is 0, 1,
it's one man, one,
and then you end up, but of course, with
you can
integral
remove the
over lambda k and L of e to the minus beta f.
Indefinite matching,
F
so
is
it's a
some
matching problem, not
effective free energy.
Bipartite
or
is you have two
energy or
different
whatever, and this is the
I look at
expression
the-
for F.
Yeah.
Now,
I think he was.
in order to calculate,
So I have a question on the
to
Gromov
find the
Wasserstein,
optimal
yes.
thing.
G,
So
the optimal assignment,
so for
we use
this
the saddle
particular
point
case, the
approximation.
problem is still like
So you can
convex.
convince yourself
So
that the
when
saddle
you go
point will be high lambda will be a real
It's
variable
not,
because you have high lambda here.
No,
high
the
lambda
difficulty,
here. So
I tell
when
you,
you write everything, you find out that high lambda
the difficulty
is
is
real,
that,
so we may
okay,
as well
in
replace
the
high lambda
standard
with lambda.
in the standard
And the saddle point
transport
equation,
problems,
you
we
have by
two
d
n
lambda
variables,
k,
which are
by
the
du,
lambda i's and the
take the
j's,
form,
which are
sum over
essentially
k
variable
x
which enforce
KL
the
equals
constraint
1,
of the g,
sum over
that
k,
the sum of the g
sum over L of xkl
Now,
equals 1,
when
sum
you
over
do
k of
the
xkl equals 1. So which means sum over lines
Wasserstein,
transport, 1, sum
you
over
have
columns
n
equals
square
1,
variable, the CIJ,
where x,
because you have to
is in
solve
fact
for
the thermal
CIJ
average of G
and the lambdas
of
and
the matrix.
So you can get
Gij,
rid of the lambdas
and it's given
but the
as
computation
H
of
complexity
quantities is
beta
not 2n. The
where
number of
H
variables
x
is not
1
2n,
over
but it's
P
n
of x
squared.
plus 1. And this is quite simple.
We haven't found
you just do
a way to
derivative with
prove
respect
the
to lambda
convexity
k
of
and
free energy.
mu L, and you get this
Because
equation.
it's a
So you
complicated,
have this quantity, which is the thermal average of G
d2f
by dxij,
with these two
dxkl, and you have to analyze
sets
that,
of
and it's
so-called marginal
trivial conditions.
So
Which
I don't know,
constrain
maybe
the
it's not
initial
convex.
G to be really
don't
an
know.
assignment matrix.
But this is the convexity
So,
of the
some
free energy
properties
that
of the
you have
saddle
at
point.
the end. I mean, when
So,
you
the first
introduce
property,
the
which is quite
delta,
important, is
the
that
free
the
representation of the delta
Hessian,
and so
so
on.
the
But
second
if I
derivative matrix
just look at
of
the
f with
bare
respect to lambda
problem with
and
just
mu,
the cost
this
function,
Hessian is negative
like,
except for a
seems
trivial
quadratic
zero
in
mode.
the
So
G,
the trivial mode
Yes,
is simply
yes,
because
let's see.
you can add
both
to
in the
something
G
to lambda,
and
a
in
constant
the
to all the lambdas, and
MIs.
subtract the same
It's
quantity
difficult to
all
know
the
because you
mu's,
have the
and
constraints.
then you
have
see
the
that
constraints,
all
right.
these
Yes,
quantities
the constraints are
conserved.
if
So
it
it
was a
doesn't
free
change
problem,
anything.
obviously,
So there is some degeneracy.
If you
and
didn't have the
this
constraints, you
degeneracy
don't need
can
to go
be
through all this
solved by imposing, for
complicated
instance,
stuff.
that lambda 1.
The problem is that
lambda
because of the
lambda
constraint,
1 equals 0.
it screws up everything.
Then
because
the Hessian
becomes
boundaries
unique,
becomes
and
definitely
the
negative.
notion of convexity is completely
And so the
lost.
maximum of the assignment problem is unique.
Yeah.
Okay.
One can show that, and all these are
there
exact
questions?
results on the saddle point approximation. So one can show that the free energy F is an increasing function of temperature, of beta.
Thank you.
So when
again,
you
I think.
decrease temperature,
My pleasure.
Thank
you very much. Thanks.
the free energy
Bye-bye.
decreases, and internal energy is a decreasing function of beta. So when you go to high beta, which is low temperature, the free energy increases and the internal energy decreases. The free energy has the form U minus Ts, and in the saddle point approximation, the free energy, the internal energy is a sum over K and L of CKL XKL, so XKL is the average G. And it turns out that the entropy has the form of a lattice gas entropy of the form XKL log XKL plus 1 minus XKL log 1 minus XKL. And an important result, exact result, is that the limit when beta goes to infinity, so the zero temperature limit of the mean field or saddle point free energy is the minimal free energy of the real system, and the zero temperature or beta infinity limit of the internal energy, which is the cost function, is the exact cost function. So, which means that at zero temperature, the free energy and the internal energy converge to exact results, to the exact values. Okay, so the way to proceed now is once you have this equation, you solve these equations by Newton-Raphson. So we have a very efficient procedure to solve these equations. And what you do is you start at high temperature and you decrease temperature in a so-called annealing procedure. So you give yourself an annealing schedule on how to modify the temperature. You start from very high temperature T and you go to very low temperature T. So one of the questions is, when do we stop? When are we sure we have got the correct assignment? Now, there is one problem that we encountered, and which is that when T decreases, one may reach some solutions where the XKL do not converge to 0 or 1. They converge to non-integer values of the variable between 0 and 1. And in that case, it is shown that the problem is degenerate. So what can show, and that's a theorem that was proven by other people before, is that when the problem is degenerate, the value to which the system converges, which are not integers, there is an integer assignment. There is a real integer assignment which has exactly the same value of the cost. In other words, it means that there is some mixture of states with 0 and 1, which give these non-integer values of the assignment matrix. And a way to see that the problem is degenerate is by looking at the entropy, which is here. In fact, you see that if x goes to 0 or 1, if your solution is made only of x equals 0 or 1 at low temperature, then the entropy goes to 0. But if x has finite values, you get a finite entropy, which is a sign of a degenerate solution. So what saves us is that when you have a degenerate solution, there necessarily is an integer solution which has exactly the same cost. And how do we obtain the optimal assignment in the case of a degenerate solution? So in order to solve the degenerate assignment problem, we showed the following. If the problem is degenerate, as I said, so there is ground state solutions with integer values of G star, so G star equals 0 or 1, which has exactly the same cost. Now, if we define delta as the gap between the optimal solution and the second best solution, so you have the optimal assignment, and then you have the next best optimal solution, then one can show that if you consider the following assignment problem, so it's a different assignment problem where you have perturbed the cost function C of KL by adding a random number. So random of K and L is a random number between 0 and 1, and alpha is chosen to be smaller than delta, the gap between optimal solution and the second best solution, divided by 2n. So if you consider this original degenerate assignment problem with CKL, if you replace it by adding this small random number, you can show that the two assignments, CKL and C'(KL) have the same optimal assignment, which means they have the same optimal assignment matrix. They don't have the same cost, of course, because the cost is modified by this, but the optimal assignment is the same for the two problems, provided that the random noise that you add is small enough. And in fact, if you scale all the entries of this CKL to be integer, if you have a finite problem and finite numbers, you can always scale them to be integer, then the gap is an integer, delta is an integer, and therefore it's sufficient to have alpha smaller than 1/2n. Okay, so this is a solution to the degenerate case. There is another problem, which is when do we stop the annealing if we are looking for the optimal solution? So what one can show is that if the problem is non-degenerate at low temperature, the matrix XKL, the matrix of assignment at finite temperature, becomes so-called Rho dominant, which means that in each row, there is one element which is larger than the sum of all others. And since the sum, by definition, when you solve the problem, the sum of all matrix elements in each line or column is equal to 1, it means that if as soon as you have a configuration, when you decrease the temperature, if in each row and each column you have one and only one element which is larger than 1/2, there is a theorem which says that you can stop and you replace each row by the dominant XKL by 1. And so the XKL, which is larger than 1/2, you put it equal to 1, and all the others you put to 0. And this is the real ground state assignment, J*KL, of the original problem. Of course, this we can prove, and it works only if the system is non-degenerate. But if the system is degenerate, as we saw before, you make it non-degenerate by adding the proper random noise, and then you use this procedure of annealing the system until you get this condition of Rho dominance of matrix element larger than 1/2 in each row and column. So the implementation is the following. So the apparent computational complexity is of order n² compared to order n³ for the Hungarian algorithm. It can be parallelized extremely nicely, and it can be run on GPU. And the storage space required for the problem is of order n². And in double precision on GPUs, because GPUs have limited memory for the moment, it limits us to cases of 30,000, n equals 30,000 by 30,000. And here is an example of performance of the method. So this is the computing time on a given computer. So for the Hungarian algorithm, as a function of the number of points in the algorithm. So this is when you do matching with a 8-core CPU in blue like this, and this is matching with a GPU, and you see that with the GPU it's extremely well parallelized, and it's extremely fast, and it outperforms the Hungarian algorithm. So this is for a distribution, Cauchy type distribution, which is just the Lorentzian distribution. But it's true for any real distribution. Now, in the integer case, so when the cost function is made of integer between 0 and 10, so this is the example that we had. So in the case when, so this is 8 CPU, it's very slow. The red is our algorithm, and you see that in that case, the Hungarian algorithm works faster, a little bit faster than ours. But the reason is that when you have integers in the range of 0 to 1, in a matrix which is 10,000 by 10,000, the subtraction procedure to put zeros essentially what you do is you start by subtracting the largest matrix element of one line to all the other lines in order to make as many zeros as possible. So when the CKLs are integer, which in a size which is small compared to the size of the matrix, the Hungarian algorithm is very efficient because it puts 0 everywhere at once. So, but in general, for generic cases, as you can see, the Hungarian algorithm really performs like NQ, and it's much slower than our algorithm. So this is what I wanted to say about assignment problem. Now I go to the more general problem, which is the optimal transport problem, which is a generalization of assignment. So the generalization is now still assume that you have bakeries 1, 2, 3, 4, 5, and you have meals A, B, C, D, E, but the bakeries don't need the same amount of flour, and the meals don't all produce the same amount of flour. So what you have to do is each meal may send some flour to several bakeries, and each bakery may receive flour from several meals. Yes. So for instance, bakery 1 will receive from A and C will send to 1, 3, 4, etc. And the condition is what we call balancing, which means that each, so we know in advance each factory or each meal has a certain total production of flour. So the sum of one of these plus this quantity plus this quantity will be fixed and given in advance. And each bakery needs a certain amount of flour, which is fixed in advance. So this amount plus this amount will also be fixed. And then there is a transportation cost for all these. And so this is a generalization of the assignment problem, which is called optimal transport. And of course, everything I'm saying is it's a discrete form of these problems, but these problems can be generalized in the continuum by replacing all these discrete objects by measures. And this has been done, and there has been tremendous literature on the subject. So the problem now is the following. So now the size of the two ensembles is not the same. You have n1 points on this side, n2 points on this side. You have a cost Cij for transportation from I to j, but each of these one can send to as many as you want, and each one here can receive from as many as you want. So the transport cost matrix, it's an n1 by n2 matrix, and the transport plan is a matrix Gij, where Gij belongs to 0, 1. It's a continuous variable. Now it's not equal to 0 or 1. It belongs to 0, 1. And Gij is also an n1 by n2 matrix. And so what is constrained now is that the total output of node I here is fixed in advance, and it's given in advance. It's m1 of I. And the total input here of any j is fixed in advance. It's m2 of j. So the optimal transport in the discrete form, the problem is to find the best transport plan to minimize the quantity curly c, which is a sum over I and j of Cij, the transport, times Gij, with the constraint that, as I say, Gij is between 0 and 1. And the sum over I of Gij is m1 of I. So m1 of I, all the m1 of i's are given in advance. The sum over j of Gij, for any j, the sum over I of Gij is m2 of j, given in advance also. So you have the total output of this one, of each of these one, which are the m1 of i's, which are fixed, and the total input of each of these one is m2 of j, is fixed also. And there is balancing, which means that the total output from one side must be equal strictly to the total input of the other side. But this is part of the given quantities because the M1 and M2 are given, and what you are looking for, and the matrix Cij is given, so what you're looking for is the matrix Gij. Okay. So the problem, again, can be formulated at finite temperature. So again, you have the variable Gij, which belong to 0, 1, and you have these marginal conditions of the summation of the distribution Gij, either on rows or column, which are given in advance. And the cost function is sum over I and j of Cij, Gij. And the finite temperature partition function of the system is given by here an integral. So the Gij vary between 0 and 1. So you have integral from 0 to 1 dGij. This is the Boltzmann factor. And then you have the constraints here for all the marginals, sum over lines and sum over columns, which are constrained to be M1 and M2. So again, you do the Fourier representation of all the delta functions by introducing the conjugate variables. And again, the Gij are linear and decoupled, so you can do the integrals. And you find that at finite temperature, the partition function can be written in the following form. It's an integral over the variable lambda k, which constrain the lines, nu L, which constrain the columns, of e to the minus beta f, where there is an effective f, which is given by this form. So it looks a bit similar to the original f. I'm looking for the assignment problem. Yes, so this was for the assignment problem. And here, it's essentially the same, except you have the M1 of k. So that's the mass of sources and the mass of the sinks, and the function here, which is just the result of the integral of e to the minus beta Gij with this and this. So again, we use a saddle point method to solve, to get this equation. So the saddle point equations on lambda and mu, and of course, again, the I lambda and I mu are real. And the two saddle point equations are just that the sum over k of jkl equals m1 of k, and the sum over L of j bar KL equals M2 of L, where j bar of KL is the phi of this quantity. And phi is this function now. So it's a function which looks like this. So you see that the j's, which are the thermal averages of the Gij, of the jkl, whatever, they are between 0 and 1, but you can reach any value between 0 and 1. Again, some properties is that the Hessian is positive with still the same problem with the trivial mode. So the free energy is concave. You can solve by Newton-Raphson using temperature annealing scheme. The free energy or eternal energy are decreasing function, and they converge to the optimal plan at 0 temperature. There is a very interesting metric property of the internal energy, which is a property which exists, which is known at 0 temperature, which is that if you have an ensemble of three, you have three ensembles of points, N1, N2, and N3. And if you have the triangular inequality, so if you have three ensembles of points, you have a cost function C12, and you have a cost function C23 for the transport from 2 to 3, and you have also a transport matrix from 1 to 3. So if you have the triangular inequality that C13 of KL is smaller than C12 of KJ plus C23 of JL for any J, so this is the, right, for any, then the optimal transport plan and the transport plan at any temperature satisfies the same triangular inequality. And this, of course, is interesting because one of the big uses of this optimal transform is to define distances between different sets of plans. And if you have this property, this allows you to define a metric between sets of points of different dimensionalities and living in different spaces. Okay, so my friend Patrick is from a computer science department, so he likes doing computer imaging. So he used the Jaffa data set, and this is a data set of 10 Japanese women which have these 7 facial expressions. And so you specify each faces by a certain number of key points. You assign, so the key points are it's a vector of features. So it's a list of 64 features. So all this is well known by computer scientists. And then you can define a distance between 2 points as just the difference, there is a metric between differences in key points. And so you can define a distance between 2 images because you have a cost matrix Cij between 2 faces. And therefore you can then classify and you can compare the data set, and you see that essentially you can classify, and these are binned faces, and you see that this allows classification of faces. And so the green part are faces which are close together. When it's blue or this color, it's the diagonal. It's when you compare it with itself, so the distance is 0. So this is shorter distances, so it's faces which look like each other. And you see that, for instance, this one is similar to this one. And so we found that these squares correspond to matching of faces where the ears are hidden. You can see on this picture that the ears of the lady are hidden behind her hair, here too, and here too. Okay, so this problem of computer vision is a problem of great interest, of course. And for instance, one of the classic problems was distinguishing a dog from a cat. So if you flip a coin, of course, you're correct 50% of the time. And 15 years ago, apparently this was the best, essentially the best one could do. Nowadays, it's about 99%. I just want for fun to show you some existing challenges, which I find quite funny. So in computer vision, dog or muffin. So this is a challenge. So of course, a human can decide whether this is a dog or muffin, although sometimes it's not completely trivial. You see the resemblance can be quite important. Here you have 3 dogs and 3 muffins. There is another famous example, which is a puppy or bagel. Okay, so now I will show you one of the problems associated with one of the problems associated with this optimal transport. And this is a cow, which is called Spot, which is a favorite of computer scientists. And when you compare 3D shapes, so maybe here I'll go back to full screen because I need there are some animations. So when you compare 3D shapes, for instance, this is a shape of SI is a spot in a certain orientation with a certain number of points with n points on SI, and TJ is the same object with a different size, and a different number of representative points. In that case, you have m points. And so you take m1 of I equals 1 over n, m2 of j equals 1 over m, n different of n, and you define a distance. The Cij is the distance, just the Euclidean distance can be between Si and Tj, between a point on S and a point on J. Okay, so now the optimal transport distance between object S and T is the minimum over all transport plans of sum over I and j of Cij, Gij. So you look for this optimal transport. And then, yes?
Sorry, just one thing. I think that we don't see the full screen now because...
okay. Just a second.
Yeah, now we see, yes, but the full screen. But you don't have animation, or yes, you do.
I will have later. Okay, when I will have the animation, I will come back to. Okay. So for one instance of the two objects, the distance is just the optimal transport plan defined by this. And the real distance that we call the distance between S and T now is, once you have this optimal transport plan, is to minimize these with respect to translation and rotation of this object S. So what you do, you calculate this optimal transport distance between S and T, and then you allow this object to move to best overlap with this, and you look by doing rotations and translations. And so it's the minimum of all rotations and translation of this distance. Okay, so this is what you would call the distance between S and T. So this is okay if you have essentially two objects which have shapes which are quite similar. Now I want to go to this problem if you assume that, for instance, you have spot and you want to match the head of spot with spot. So you have, of course, much less points here than here. And so so now I play because there is some animation. And so when you do the algorithm that I showed before, what it shows is the minimization of the system is trying to minimize the overlap of the head with the full cow. And of course, it's impossible because you have because of the weights, the masses, all the masses are given here. You have all the masses over here. So the system will necessarily try to match some points of the head here, with some points of the body of the cow. So it's,
I think we don't see the animation, but
you didn't see the animation?
Because for us, you didn't switch to the play mode.
Can I try like this?
Yes, now I think it should.
Okay.
So, yes.
So this is how it goes. So it tries to match and doesn't match, and it will stop at some point. And this is okay. So this is the best the system can do. Can you see back? It's okay now?
Yes.
Okay. So this is the best you can do because, as I said, there is some mass associated to the body of the cow, and the head here will try to match in the transportation some of its point with the body here. So in order to circumvent this problem, we have introduced optimal transport with masses. And so this is the original optimal transport. The idea now is to leave, not to assume that these masses are given, but that the masses will be decided by the system. The system will introduce the mass by itself. So the only constraint is that the masses are positive, and the sum over I and j of jij should be equal to 1. Okay, so this tells you there is a total mass which is shared between S and T, between the two objects, and this has to be fixed. Now, if you consider the problem like this, as it is, it will, and if you let M1 and M2 be completely free, then it gives a totally wrong result, because essentially it will pick one point in one ensemble, one other point in the other ensemble. It will put all the MIs, M1 and M2 to 0, essentially, and you will get a completely useless solution. So the way to do is to add a penalty term here, which is proportional to the square of the sum of the square of the masses, and minimize this object instead of minimizing just this object. And you have this constraint that the sum of the M1 of I equals the sum of M2 of J, and the total sum is 1. So the partition function is again an integral over the Gj, KL. Then we have an integral over the masses M1. So each mass is integrated from -infinity to +infinity. The cost function now is the standard cost function plus the Gaussian, the quadratic penalty. These are the two constraints. Constraints on the lines, constraints on the columns. And this is the global constraint that sum over K and L of JKL equals 1. Right? This is the balancing condition that the sum over K of M1 of K equals sum over L of M2 of L. So you see that once you do this exponentiation, the M1 and M2 can be integrated exactly because they are Gaussian, and we get an effective free energy, which has this form. So the free energy, this is the term that we had already in the unbalanced case, but what replaces the other terms are these two terms. And now we can do a saddle point approximation, and the equations take a form which is that the average phi, so the thermal average phi, G, is phi of this quantity, so it's with the same function phi as in the standard optimal transport, but the marginals are given by this expression. And so you have to solve for lambda and mu so that you solve all these equations at once. So I give you some example. So it is what we call optimal transport with variable masses. So if you take, so this is a man, this is a horse, and this is what the Greeks introduced, which is called a centaur. So it's a half man, half horse. And if you look at image comparison, if you take a centaur and try to match it with a horse in standard optimal transport, you see that the system will try to match not only the horse part of the centaur, but also the human part to the horse upper part of the body. Same for the man and centaur. You have a matching which goes like this. Now, when you go to variable mass, automatically the system will put 0 mass in the upper part of the body for the, we'll put 0 mass here, and we'll concentrate all the masses here to the parts which are similar. And same here, the system will put masses only on the upper part which are similar and not on the lower part which are quite different. And now if you look at this, so can you see this animation?
Yes.
Okay, so here automatically the head will be matched to the real head of Spot, and the distribution of masses, if you take the whole Spot, you see that only one part which corresponds to the head, once you solve the equations, only one part will have non-zero mass and all the rest will have 0 mass. whereas the head, which is here, has a non-zero mass everywhere. Okay, so this was to show the efficiency of optimal transport with variable masses. I want to conclude now with something on which we have been working more recently with Patrice, which is the Gromov-Wasserstein distance and the corresponding Gromov-Wasserstein optimal transport. So the idea is to do optimal, so in the standard optimal transport, the matrix, the cost matrix is given in advance, and it defines, it's given by someone outside. The Gromov-Wasserstein optimal transport uses something which is different, which is a cost function which depends on G itself. So, so if you have two sets of points of different cardinalities, and X and Y, and 1 and 2, whatever you call it, you look for a matrix Gij such that you minimize U equals Gc with the cost function being given as dii prime minus d1 ii prime minus dy jj prime to the power p gy prime g prime, with the same constraints of given mass m1 and m2 and balancing. And of course, this is extremely powerful because you can have different metrics on each ensemble. You can have different number of points, and essentially the system tries to pair points for which the distances are as similar as possible. Well, that's what the minimization does. So if you do it at finite temperature, again, what you do is you write it E like this, the cost function like this, and what you do is you constrain by a delta function this, in addition to the usual constraints on the marginals, you constrain C to be equal to this by this C hat. So this is the conjugate variable. This C hat constrains Cij equals this. And then you can do exactly the same, and you get saddle point equations, which are very similar to the standard optimal transport, but with a self-consistency condition for the cost function, which is given in terms of the transport G bar. So you have to solve this set of equations, so which are very similar, these three first one as the optimal transport, and this one is a new self-consistency condition. So the idea is to do a temperature annealing from high to low temperature. So you start at high temperature, you go to low temperature, you start with an initial Gij bar. From this Gij bar, you calculate a Cij. From this Cij, you solve for lambda and mu. Once you solve for lambda and mu, you have the new Gij. With this new Gij, you recompute the cost, and etc., and you iterate. And then once you have converged in this nonlinear procedure, you can go to lower temperature and you iterate the process. So this procedure in principle works, but it can be very slowly converging, and we're working currently to try to find a way to improve this method or find other ways to improve. Of course, when you do the annealing, you always keep the values of the G at the last temperature as initial value for the new temperature, for the lower temperature. Okay, so I'm essentially done. And just to conclude, so I want to emphasize a few things. So statistical mechanics is obviously a natural framework to study assignment, optimal transport problems, and more generally, combinatorial optimization problems, as has been seen in the past. Optimal transport allows to define a distance between objects which are living in different spaces with different cardinalities. And we can do not only compare full objects, but we can do also local matching or parts of the object by using the variable masses. This is very important, for instance, when you want to compare for instance, one thing for which I'm quite used is proteins. If you look at shapes of protein, because of evolution, you have some parts of a protein which are very similar to some parts of other proteins in 3D, and so proteins are made of objects which are stuck together, and so you cannot have a global matching. It's not very efficient, so you need this local matching to be done, and one can use variable masses for that. And the most promising object is, of course, this Gromov-Wasserstein, but at present we cannot implement it in an efficient way, and we are limited to very small sizes. And thank you very much for your patience.
Thank you, Ali.
Okay.
We have time for questions.
Okay, I had a question actually. I don't know if you hear me.
Yes.
Yes.
Very nice talk. I was curious about the comparison of this algorithm with the message passing algorithm like belief propagation or auction algorithm for assignment problems. So because the comparison was with the Hungarian algorithm, but I was just curious to know about this, for example.
Okay, so actually for the assignment algorithm, the fastest known algorithm was the so-called invisible hand algorithm. And the invisible hand algorithm is an algorithm based also on statistical mechanics, which was introduced in the late 90s. And apparently it's the fastest algorithm. I have some, actually, I could. So our algorithm is a bit faster than the invisible hand algorithm. It works only for assignment. It doesn't work for, sorry. Yes, okay. I can show you. Sorry. Okay, no, I don't have. Okay, no, it's not this. Sorry. Yes. Okay. Sorry. Okay. So this, so I will share. How do I share again? I have to stop. I have to stop sharing, right?
Yeah, and then you share the new one.
How do I stop? How do I stop sharing here? Okay, maybe. Okay, fine. I found it. Okay, so now I share. No, where do I share?
Same place.
Sorry.
Like,
oh yes. Okay.
Down.
And
the webcam.
Okay. So what to share? Okay. Okay. The same screen. Share. Okay. Can you see this?
Yes, it's loading. Yes.
Okay. So the best algorithm. So the best algorithm for matching and also for optimal transport is the so-called IHA, invisible hand algorithm. This is the best algorithm as of now. And this is a comparison of so Sinkhorn is another widely used algorithm. Red is this invisible hand algorithm, and black is our algorithm. So we do a bit better than invisible hand, but this is only for assignment. It doesn't exist in optimal transport. Now okay, so this is as a function of temperature. Of course, as a function of temperature, some algorithms become extremely slow. but still we are still better than the invisible hand. I think the message passing and all these are not, as far as I know, they're not the fastest and the most efficient algorithm. I'm seeing something very interesting, which is a fractal.
Yeah.
Okay, so I should stop. Sharing the screen, right? But again,
Okay. Okay. Thanks.
okay. Yeah, I don't know how to stop sharing the screen.
I think if you there is something like I don't know. I actually I see in your screen stop sharing just right above the toolbar.
Just above.
Yeah, just above like time machine, the time machine icon. Down.
Ah,
Yeah.
stop sharing. Yes. Okay. It was nice though.
Okay. Are there other questions?
Yes.
Actually, yeah.
To answer, François David is not here. He says that I allow polygamy. It's not matching. It's not polygamy. It's one man, one woman. But of course, you can remove the sex and have completely indefinite matching. So it's called matching problem, not bipartite. Bipartite is you have two different sets. I look at the.
Yeah, no, I think he was the only one. So I have a question on the Gromov-Wasserstein
yes.
thing. So when you for this particular case, the problem is still like convex. So when you go to
it's not clear. It's not. No, the difficulty I tell you. The difficulty is that in the standard optimal transport problem, you have two n variables, which are the lambda i's and the mu j's, which are essentially variable which enforce the constraint of the g's, that the sum of the g's are 1. Now, when you do the Gromov-Wasserstein transport, you have n square variable, the Cij, because you have to solve, in fact, for the Cij and the lambdas and the mu's. So you can get rid of the lambdas and the mu's, but the complexity is not 2n. The number of variables is not 2n, but it's n square. And we haven't found a way to prove the convexity of the free energy because you need it's complicated. You need D2F by dxij, dxkl, and you have to analyze that, and it's not completely trivial. So we don't know. Maybe it's not convex. We don't know.
But this is the convexity of the free energy that you have at the end. I mean, when you introduce the delta, the yes, free representation of the delta and so on. But if I just look at the bare problem with just the cost function, this is like seems quadratic in the G, right?
Yes, yes. Let's see.
So it's quadratic both in the G and in the MIs.
It's difficult to know because you have the constraints.
You have the constraints, right?
Yes, the constraints are. If it was a free problem, obviously it would be trivial. If you didn't have the constraints, you don't need to go through all this complicated stuff. The problem is that because of the constraint, it screws up everything because you may hit the boundaries and the notion of convexity is completely lost.
I see.
Yeah.
Okay. Thanks. Are there other questions? Okay. No. Thank you again, Ari.
My pleasure. Thank you very much. Thanks. Bye-bye.
See you.